In today's video, we're going to work through a sort of full example problem involving Newton's laws and forces and that. If you recall, the last few videos we've looked at how to quantitatively model some of the forces we've been talking about: gravity, friction, drag, and that. Before that, we looked at how to identify forces, how to set up situations and analyze what's involved. Today, we're going to put it all together and work through one of my favorite examples of problems like this. The problem is essentially, it's written here, but essentially what it is I have some, I have a table with, we'll say, a book on it, right? And then I slowly start to tilt that table and till it's up at an angle. And eventually I'm going to get that table tilted so much that that book's going to start to slide down the table. So if I do this and I do it and I measure that angle that I'm at, and I measure the angle where that book starts to slide, I can then ask, well, what is the coefficient of static friction? One of the reasons I like this problem is because it sounds like there's no possible way you're going to be able to do this. I mean, there's the book. I haven't given you the mass of the book. I haven't given you the size of the book. I haven't given you anything. The only thing I've really said is there's an angle that this slides at. But it kind of shows how we can analyze these situations using forces and the sort of techniques we've learned and get a lot out of the problem. So I'm going to go through here and sort of remind us of the problem solving strategy that Knight describes. The first thing in that strategy is to identify the forces. Whenever we're doing dynamics problems and we want to work on out what the forces are, we need to identify the forces. The way we do that typically is draw a picture of the situation. I have my book on my tilted table, and we circle the object we're concerned with, right? Then we look at anything that breaks that circle is in contact with the object we're talking about. So in this case, I'm talking about the book. That's the object I'm trying to describe. I circle it. The only thing that's, going through that circle is the surface of the table. So I know that surfaces can apply two types of contact forces: normal forces and a frictional force, right? So I have to worry about those two things. There's nothing else touching that object, so I know there are no other possible contact forces that I need to worry about when I'm describing that book. I am presumably on Earth, so we're going to look at long range forces and next, and the only long range force we're concerned with is gravity. So I've identified the three forces involved in this problem. Finish the first part of that force, of that problem solving strategy. The next thing I'm going to want to do is sort of set these up visually in a free body diagram, right? So I'm going to redraw this picture, and I again like to draw the table or the slant it's on just to sort of orient my picture. But I've got my book on that table, and I know the directions of these forces because we've been discussing them and we're familiar. We know the normal force is always going to be perpendicular to the surface, so there's going to be a normal force coming off that surface at a right angle. We know gravity is always straight down this way, gravity. And we know the friction force. We're looking at static friction in this case, right? Because I measured that angle as the angle where it went from standing still to moving. So this is sort of, you can think of it as this was the angle that was the last angle where that book stayed still, right? Up to 25 degrees, that book stayed there. I go further, it starts to slide down. So that friction is going to be going up the ramp, preventing that book from sliding down and keeping it stationary. So now I've drawn my free body diagram. I've completed the second sort of step in this problem solving strategy. The next thing, I like to write it as a separate step, is to pick an appropriate coordinate system for my free body diagram, right? Ultimately, we're going to apply Newton's second law to this situation. We're going to have to add vectors and everything. We're going to have to split them into components. We need a coordinate system to do that. Now, for this situation, I can choose any coordinate system as long as those x and y directions, the directions I choose, are at a right angle to each other, any is possible to do it right. However, I can make my life a lot easier if I choose, I should probably have done this in a different color, sorry, let's use blue. Um, if I make that direction X and that direction Y, we'll say, we'll tilt that coordinate system up at the same angle as that the ramp's tilted at. The reason that's going to make my life easier is if you think about it, we're going to be using this coordinate system to break these forces into components. And if I align my coordinate system this way, well, the normal force is all in the y direction. The friction force is all in the x direction. And the only force I'll have to break into components is gravity. So I only have to do those sort of trig equations to figure out things once. Whereas if I had chosen a different coordinate system, say x and y, in those directions, I would have had to do trig to figure out the components of the normal force and the frictional force. And there's just, I've doubled the amount of sort of work I have to do to figure out those components. So a little bit of thought here and practice with these problems will help us, get familiar and make these decisions sort of quicker. Can help us choose an appropriate coordinate system for the problem. The fourth one, which has a lot of the math and everything in it, but really all we have left to do is apply Newton's second law in that coordinate system. So we apply Newton's second law in that coordinate system. So if we're looking at this, we're going to have, an x components and y components to this problem. We're going to have forces in the x direction and in the y direction. So this is going to be our net force in the x direction is going to be equal to the mass times the acceleration in the x direction. And likewise, for our y component, the net force in our y direction is going to be equal to mass times acceleration in the y direction. And hopefully we've kind of got comfortable that the left side of this equation is essentially everything we know about the forces. That's going to come from this. Our free body diagram is going to tell us what those forces are. There's going to be the normal force, the friction force, and gravity. And that's everything on the left. And our acceleration we get from knowing how the description of the motion, if it's given in the problem. So we have three forces, so there's normal force in the x component of the normal force. There's the x component of the frictional force, and then there's the x component of gravity. And these are going to be equal to mass times the acceleration in the x direction. Yeah, I'll just write it out again. Now we can start to think about, so this is, I've just rewritten this equation, acknowledging that there's three forces I have to worry about. But now we can actually look at these and start to plug in things, quantitative models for it. The first thing is, what's the x component of the normal force? Well, x in our coordinate system is up and down the ramp, and the normal force is perpendicular to that. So there is no component of that normal force in the x direction. So that's just 0, right? The force of static friction is entirely in the x direction. So this is just Fs. It's the force due to the static friction. It's in the positive x direction, so that's just plus Fx. And the gravitational force. This one often can confuse people a bit because typically we think of gravity's up and down. It's all in the y direction, but we've tilted our y direction and our x direction. So if we were to draw the components in that direction, in that x and y direction, these are the components. This is the gravity in the y direction, and there is actually a gravity force due to gravity x component that's this way, right? So we have components of gravity in the x and y direction. Turns out this angle theta is the same angle as that it was tilted up at. And you can sort of see that. If you think about when it's flat, if we have that flat surface, that y direction and x direction are like this, and sorry, that's a y. And as this table gets tilted up at some theta here, this y direction is going to tilt that way and go that way. Gravity is a straight line down here for both of those. Uh, so if I draw that vertical line, that's the direction gravity's in, this angle here is growing the same way this angle here is growing as that side comes up. Hopefully you can see that. There's a lot of, we could spend a lot of time doing trig in the synchronous sessions. If you're having trouble seeing how these angles are equal, I can definitely spend some time and do some similar triangles in that to get those thetas. But for now, I'm just going to say, hopefully you followed this and that these angles are the same, and that angle's theta, and we're going to need that to break out our components. But the point is, knowing that this angle here is the theta, this x component in this right angle triangle, this is our right angle, is, well, sine theta, if we remember our SOHCAHTOA, sine theta is equal to opposite over hypotenuse. For this triangle, our hypotenuse is the force of gravity, mg, and our opposite angle is the force of gravity in the x direction. This is the opposite side of the triangle. This is our hypotenuse. We know the magnitude of that force vector is mg. So mg sine theta is equal to our x component of gravity. That gives us the magnitude of this side of the triangle. It is pointed in the negative x direction. You remember, this is our positive x direction, so this arrow is pointing down the ramp. So this is going to be negative mg sine theta. And the acceleration, again, we're looking at the angle, the last angle where this object was stationary, so there is no acceleration. It's still standing still. So this is going to be equal to 0. We know the force due to static friction is equal to mg sine theta. We knew one more thing on this side. We also know, since this is the point where it's the last point where that force of static friction can keep this book stationary, we know that our force of static friction is actually equal to the maximum possible force of static friction, which, if you recall from a few videos ago, is the coefficient of kinetic friction times the normal force, right? So we can make this substitution in our equation that we got from Newton's second law, and we get mu s times n is equal to mg sine theta. And what we've got here is the x component, the x direction of Newton's second law gave us an equation here that we can use to sort of solve some unknowns. The problem is we have two unknowns right now. We don't know the coefficient of static friction, and we don't know the normal force yet. So we have to find another equation to help describe this, to sort of sort that out. And what it is Newton's law in the other component, in the other direction, right? So we can do the same thing we did here with the y component, right? We're going to have a normal force in the y direction, plus force of static friction in the y direction, plus a force of gravity in the y direction is going to be equal to mass times acceleration in the y direction. Again, from my free body diagram, I know these are the only forces that are involved. I'm just looking at their y components and plugging them into Newton's second law. Looking at this again, the normal force in the y direction is just the total magnitude of the normal force, and it's in the positive y direction. So I have the normal force. Static friction, again, on our tilted coordinate system, this is entirely in the x direction, so it's equal to 0. There's no y component of that static friction, so that's just plus 0. And gravity, we need to look at this y component of gravity, much like we did with the sine here to figure out the x component. In this case, it's going to be cosine theta is equal to gy over mg, because mg is the hypotenuse, gy is the adjacent side of that triangle. So I know my y component of gravity has a magnitude of mg cosine theta, and it is pointed, in the negative y direction. It's pointed down like that. So this is going to be negative mg cosine theta. Just like with the x, this object's stationary. It's not moving up and down in the y direction in any way, so our acceleration is also 0. So now with this, we can actually solve, bring the mg cosine theta to the other side, we can solve for what our normal force is. So this is a second equation we've got from Newton's second law in the y direction. And now we have two equations and two unknowns. We can solve this system of equation. We can take this normal force that we got from looking at the y direction and plug it in to the equation we got over here from the x direction. What that means is if we do that, we get the coefficient of static friction times mg cosine theta, which we just showed our normal force is equal to mg sine theta. And you can start to see things cancel. We divide both sides by mg, those cancel. We can bring the cosine theta to the other side, and we get the coefficient of static friction is equal to sine theta over cosine theta. And we know the angle, so we can solve that. We can also simplify this. That's actually equal to tan theta. And if we plug in 25 degrees into that, we get a coefficient of static friction of 0.466. And we've answered our problem. Right? Something that at the start of this probably seemed really ridiculous. We probably didn't feel like we were given enough information, and we might have frozen up if we were just asked this on our own. But one of the things that I want to keep stressing in this class is this strategy is always a good way. It's a brute force way to just slowly start analyzing these sort of force problems. Especially pragmatically for assessments in that you can get partial credit all the way here, even if you didn't make it all the way to getting that solution. If you can ID all the forces, you know kind of what's involved in the problem, and drawing your free body diagram. If you get to here, you've sorted out, you've set up your model and how you're going to solve this a lot. The rest of it is mostly math, right? You have some unknowns that you're trying to sort out, and applying Newton's second law is going to give you equations that can be used to solve those unknowns, right? You're going to get one equation for each dimension of your system. So this is a two-dimensional problem. We have x components and y components. Newton's second law gave us one equation for the x component and another equation for the y component. And we had turns out we had two unknowns in this problem, and these two equations were all we needed to solve that. So hopefully we'll see in the synchronous sessions and as we work through homework and problems like this that this sort of setup and just stepping through these processes can really help us solve essentially any of these Newton's laws dynamics problems we're concerned with. So think about that, practice it, and if you have questions, bring them up in the synchronous sessions or email me, and I will talk to you then.